Hi students, welcome back to class, Oceanography. Lesson 4 is pertaining to the origin of Earth. We have to go through this so you'll understand how Earth came to be, and then that leads us into a discussion of the origin of the ocean, our topic. So we start with something called the nebular theory, which explains the origin of the solar system. Phase 1, looking at the diagram to the right, the sun and planets condense from a mass of dust and gas, what we call a nebula, from about 7 to 4.6 billion years ago. So this process, this first phase, took a lot of time. In phase 2, gravity starts to contract that nebula. As that occurs, you'll have conservation of momentum, which causes spinning of the condensing nebula. In the very middle of this, you'll have a star starting to form because of the intense heat. And then around that center of the condensing nebula, you'll form a much cooler disk of matter. And that's related to the inertia from the conservation of momentum. So the whole thing is starting to spin. With phase 3, shown by the two yellow arrows, those two phases on the diagram essentially the same. Here, we're looking at the disk of matter. Solid bodies, including the planets, moons, and asteroids, cooled and condensed from that disk. So important step to form planet Earth. With phase 4, down at the bottom left, we now have an orderly solar system, planets in stable orbits around the sun. So here's that diagram, steps 1, 2, 3, and 4. You should have a grasp of it. So again, let's just do a quick review. Phase 1, we've got our nebula, and the arrows indicate that it's starting to condense due to gravity and starting to rotate, conservation of momentum. At phase 2, now it's getting hot in the middle. We're starting to fuse hydrogen atoms together, forming helium. So we're starting to develop a star, and we're getting that disk of matter, relatively cool matter, forming around that new star. At step 3, we've got our sun in full flame, full blaze. It's called a protostar at this stage. It's brand new. And then we're getting a distinct disk, and we're starting to form individual bodies. And at step 4, after a period of several billion years, we have the orderly solar system that we have today, with the sun in the very middle and the planets orbiting around the sun. So that's the nebular theory diagram. So with regard to Earth, solid Earth formed as a matter condensed into a large rocky ball. We call that process planetary accretion. To accrete means to bring together. Accretion mostly finished, we think, around 4.6 billion years ago. So this illustration, not a photograph, this illustration tells us how this probably came about, with big rocks, meteoroids, asteroids, being attracted to Earth, and one by one slamming into the planet. So that's the accretion. No doubt early Earth was homogeneous throughout. That means it was not layered, it was just all the same throughout. And it was probably very hot due to that accretion process. Here's an excellent illustration showing a large impact, and the heat generated from that helps to keep Earth's surface relatively hot. You can see some of it shown as being molten liquid rock, and other is fairly cool solid rock. About 4.43 billion years ago, Earth collided with a Mars-sized body. That event probably melted Earth throughout. So this is a major event for our planet. Also note that debris from the impact was thrown into Earth orbit, and it condensed to form the moon. So this age of 4.43 billion years for this event is taken from the age of the oldest moon rocks collected by Apollo astronauts back in the 1970s. Since Earth was in the molten condition, heavier elements like iron and nickel were pulled to Earth's center by gravity. This process displaced lighter elements, oxygen, silicon, aluminum, potassium, calcium, and others toward the exterior. So here we have an image that tries to illustrate the sinking of the iron and nickel toward the center and less dense elements moving toward the exterior. So this process we call planetary differentiation. It's actually a good term because it describes what happens to the planet. It becomes different. So what we wound up with, due to planetary differentiation, was a planet that was no longer all the same or homogeneous. It was now stratified based on composition and physical properties. So looking at the image on the left, a homogeneous Earth, now with iron sinking to the center, lighter matter toward the exterior, and the product on the right with the crust and the mantle and the core in the middle. And here's another image showing our stratified or layered Earth, crust, mantle, outer core, inner core. So here's a sketch I would like you to make on a sheet of paper. We'll use this to learn more about Earth's layered interior, and we'll come back to this when we talk about plate tectonics. So go ahead and take a moment, sketch this out. Now that you have that sketch, I'd like to list the main elements present within the core, the mantle, and the crust on the diagram. So one thing of special note is that both pressure and temperature increase as you go deeper within the planet. These variables control whether a zone of Earth's interior is solid. If it's solid, then the effects of pressure override the effects of temperature. Or does it behave as a liquid? In this case, the effects of temperature would override the effects of pressure.